Good morning, everybody. Today is Codeforces Educational Round 94. As usual, solutions will be available at the end of the video. And here's the screencast. Let's begin because it's already started. So we have a binary string where each character is either a 0 or a 1. Two strings are similar if they have the same character in some position. We have integer n. We have company. We have some integer n and some binary string of an odd number of integers. You have to construct a binary string which is similar to all of the following strings. The first n, the next n, etc. So, whatever this last character is part of all of the strings. So we'll just have all that character. So let's do that. Int n equals this number. Array line equals this. Sys out line at n minus 1. And then a new line. So 1, all zeros. I think that's right. This should be all zeros as well. This should be all zeros. Okay. Looks good. Let's submit. Awesome. On to problem B. We're playing an RPG from 2010. We want to get as many resources as possible, so we're going to steal them. You decide to rob a town's blacksmith and take a follower with you. You carry at most P units and your follower at most F. In the blacksmith shop, you found some number of swords and some number of axes. The sword have a certain weight, and each axe has some other weight. You don't care what to take, since each of them will melt into one steel ingot. It's the maximum number of weapons you and your follower can carry out from the shop. Why would you not just take the whichever is smaller? Oh, I guess you can't take more than the max of them. Interesting. Yeah, okay. So well, you're going to take as many as possible of whichever one is lighter. But then the question is, who do you distribute that to? I suppose we can brute force how many we distribute to each person, right? So if we have 10 to the 5th, like whichever one is lighter, we have at most 10 to the 5th of those. We say, how many of those do we give to person A? Or really, we can just like brute force how many, yeah, brute force how many lighter ones you have to the first person, and then you're good. Alright, so we don't need any math for that. We can just start typing, I think. So first we need int cap1 equals this, cap2 equals this. int n swords equals this, n axes equals this. We need the weight of each sword and axe. And then, oh, I suppose we can just brute force the number of swords, and that's fine. So 4 int s. Oh wait, we can't do that yet. So if s weight is bigger than the axe weight, we should swap them. Okay, so now swords are cheaper. So 4 int to keep equals 0 to keep less than or equal to the number of swords to keep plus plus. So if we can't even carry these, then we're in trouble. If to keep times the sword weight is greater than cap 1, long answer equals 0, print the answer, and, well, okay, so then int o keep equals math.min, number of swords minus how many we have left. And the number he can carry. So now we have like my weight left. That will be cap 1 minus to keep times the sword weight. And also the number he has left. That will be cap 2 minus how much he keeps times the sword weight. Then into my axes will be my left over number of axes minned with the number of axes. This isn't number of axes, this is axe weight. Int his axes will be math.min of his left over the axe weight and the number of axes minus the number of axes that I have. Okay, ans equals math.max of the answer, or how many swords I keep, plus how many swords he keeps, plus how many axes I keep, plus how many axes he keeps. $11.23 looks good. Overflow I don't think is an issue. Is this a problem? I don't think this is a problem. Because if S weight is big, then this is small. All right, on to problem C. Binary string reconstruction. Wait, we've already seen this, haven't we? No, we haven't. You have binary string and an integer x. You want to build a new string of n characters where the ith character is chosen as follows. Was that something I was supposed to read? I didn't even check. Usually they're for problems I've already solved. Yeah, okay, don't care. If the character, this thing exists and is equal to 1, then SI is 1. Okay. If the character exists and is equal to 1, oh, well, this is not what I expected. So if you go back x characters and there's a 1, then it's a 1. If you go forward x characters and there's a 1, then it's a 1. If neither are true, it's a 0. So what happens here? You're given the string s and then the integer x. So here we're given this thing and the integer 2. So you have this. If you go forward 2, you have a 1. So this is a 1. Now you have this. So you go forward another 2, you have a 1. Or this, you go forward 2, you have a 0. I see, yeah. So we'll make everything 1s and then we'll turn things to 0s and then check. How about that? I think that should be fine. Yeah, okay. Sounds good. Read in the string, also read in x. So we've got the length. Now for, what is going on? No thank you. Just go away. Is it Boolean? All right. So char array ants equals new char array n. Raise dot fill this with 1s. The character 1, I guess. Then we just need to mark all the 0s. Okay, now let's just check if it works. For in diagonal 0, I less than n x plus. If s at I is equal to a 1, if not legal, or if legal at I minus x n, ants at I minus x is equal to 1. Continue. Same thing with plus. Otherwise, works equals false. If not works, sys out -1. Otherwise, sys out the answer. Looks good. Holy cow, lots of solves. Alright, on to problem D. You're given an array of a bunch of integers. Count the number of tuples, so the number of groups of 4 numbers, where they are increasing, and the first pair equals the second pair. This sounds kind of interesting, actually. Conveniently. N is very small. So let's see, what can we do for this? Well, we can do something like this, I think. Give me some whiteboard space. We can do, if we have a bunch of, if we've got a bunch of positions, say we know this position here and this position here. Let's say this is like we have an I over here somewhere. This is position J, this is position K, and then we have an L over here somewhere. If we brute force what this J is and what the K is, then we just need to know the number of I's in this side here and the number of L's on this side here. Yeah. All of the values are small as well, so it should be easy enough, it looks like. Very good. Oh wait, IK. I equals K and J equals L. Yeah, same thing, just look in different arrays. So int n equals this, int array A equals read array size n. For int L equals 0, L is less than n, L plus plus. For int R equals n minus 1, R is greater than L, R minus minus. Int array L counts equals new int array n plus 100, I guess, or something. Then we need an R counts array. And now L counts at A at L plus plus. Increment the number of counts of things to the right of the right pointer. And we need some answer. So long ans equals 0. Sys out the answer. And then what do we do here? The left things that match the right pointer and the number of right things that match the left pointer. They're independent, so you have to do both. Looks good. Move on to E, I guess. Yeah, that's kind of the plan. You have a multi-set containing several integers. Initially, it contains A1 elements equal to 1, A2 elements equal to 2, and AN elements equal to n. The order of the elements doesn't matter because it's a set. You may apply 2 types of operations. You can choose 2 integers, L and R, remove 1 occurrence of L and 1 occurrence of L plus 1, all the way up to 1 occurrence of R. This can only be applied if every number from L to R occurs at least once. You can also choose two integers I and x and remove x occurrences of I from the multiset. I see. What's the minimum operations to delete all elements from the multiset? Good question. I like it. I don't know. It's not super clear how to do it. So you only use this operation at most once per index. There's no reason to do anything more than that. I guess we could do a DP. So we could do a DP where our state is which index we're at and how many, like how deep we are, basically. And then we have two transitions. We can either, well, we'll always have to decrease how deep we are, at least. Then we can either increase it to the maximum, or we can use the other way to get rid of this position. So yeah, let's just code that real quick. Is it single test case? It is. So n equals this thing, array equals some array of size n. We'll have a DP, static int go. Yeah. Int which index we're at, and then also the current depth. Oh, the depth is interesting, because we might need to coordinate compress it, I guess. I suppose we don't really. I suppose that we can just use the index of the depth. So it'll be n by n. Yeah, just that. Okay, so we have our DP, and now it's initially all negative ones. The ants will be go at 0 with 0 depth index. Oh, that's not true. So index 0, depth index will be n. Yeah, okay. Because that'll just be 0, so we start at depth 0. So if index is equal to a.length, then return 0, because we're at the end. Otherwise, we have a couple things we need to do. So if, well, then return if dp at index, depth index, is not equal to 0, -1, return it. Otherwise, return this equals the answer. So initially, int ants equals 1 plus go. example of some stuff. So we have a couple of cases. So if A at depth index is less than A at index, go to the index plus 1, and then the depth index, or the same depth index. So this would just handle this position in particular. Alternatively, ans equals A at depth, or A at index minus A at depth index. So we can increase the height to whatever it is here, plus go index plus 1, the index. Otherwise, we might as well just decrease it to our index anyway. Turn go at index plus 1, index. DP is null, huh? Really? Oh, right, next set of bounds for length 4. Oh, A dot length minus 1. Alright, hang on. Now you're telling me this answer is 4, really. If A at depth index is less than A at the current index, so this means the height increases. Surely these are the two transitions, right? What else would they be? It's just these two things. Oh, it goes to the min. Good. Or am I memoizing? Yeah, looks fine, looks fine. Submit E. If this is too slow, it shouldn't be, but if it is too slow, we can probably optimize it a bit. Alright, so now we read both of them because there are 2 problems left, and those are all we need. We're probably doing not too bad scoreboard-wise, right? I mean, we're pretty much just flying through it. Yeah, 8th place. Not bad. Not bad. For a bunch of easy problems. Usually I'm pretty slow on easy problems. Okay, you're given an integer value x in a string consisting of digits 1 through 9 inclusive. A substring of a string is a continuous subsequence of that string. I thought it said continuous substring at first. That's why I was so hesitant to read it. Let this be the sum of digits in the substring. Let's call a substring x prime. If the sum is x, and also there are no values, L2, R2, where you can pick a substring of the current substring. The sum of the values isn't x. And x is divisible by the sum. Okay, there are no zeros. That makes sense. So we pick some substring. All that ever matters is the sum. So basically we pick some substring where it is not divisible by any substring inside of it. You're allowed to erase some characters. If you erase characters, the 2 resulting parts will be concatenated without changing the order. With the minimum number of characters you should erase so that there is no x prime substrings in it. You're telling me there are no x prime substrings in the substring 13? Oh, that is wacky. Yeah, I guess that's true for 13. Because if you have picked 13, then you can pick a 1. If you pick a 3 or a 1, that's it. In all other cases, you're not allowed to have a 1. Can this length possibly be bigger than like 10? You run into some pigeonhole principle stuff, don't you? Wait, what does x mean? It seems very brute forcey. What is x here? Oh, they have to be, it has to sum to this amount. Weird. Yeah, okay. So we need, like, the question is, you need to modify all substrings in a certain way so that it sums to this value. I think I can do it in 1,000 times 2 to the something. Maybe it's like DP with pruning or something. I don't know, it's kind of hard to imagine. Let's read G first. He's playing yet another strategic computer game. In this game, he leads an army of mercenaries. He wants to gather his army for a quest. They're end mercenaries for hire. The army should consist of some subset. The ith mercenary can be chosen if the resulting number of mercenaries chosen is not less than L. Otherwise, the quest will be doomed. Furthermore, M pairs of mercenaries hate each other and can't be chosen to go on the same quest. How many non-empty subsets should he consider? So you have a whole bunch of mercenaries and up to 20 pairs that dislike each other. Then you're given all the pairs. The question is, how many subsets are there? That work. Yeah, so the up to 20 pairs is obviously important. Well, maybe not. I mean, clearly it's important for the intended solution, but I don't see why it's necessary yet. It just seems like some kind of arbitrary restriction at the moment. Yeah, so I guess interestingly, this means that there are quite a few mercenaries out there. Like, you have 20 pairs, right? But that gives you at most 40 mercenaries that are special. So you've got a bunch of, like, just totally content mercenaries, but then you might have up to 40 that have some edge connected to them. 40 is a big number. It's big enough that you can't do 2 to the n, at least. Which strikes me as it seems similar in nature to problem F. Yeah, it looks like here's the wall, so easy all the way up to this. Yeah, 7-second time limit. It's interesting. So what can we do here? Maybe let's draw a picture. Are there any other restrictions I'm not reading here? Wait. Oh, it's even harder than I thought. So, yeah, the ith mercenary is an entire range of mercenaries. He's like the number of people on my team has to be somewhere in this range. Yeah, alright, well, that's fine, I think. Let's not even worry about that part for the moment, because the rest of it seems hard enough. Even if you just have something that's like this, maybe? Oh, okay. So, like, maybe we could brute force the number of people. If we do that, we've removed the constraint of who can come and who can't. We just need to see, can we, or like how many groups of this many people can we find? We also have to do that unusually quickly, but that's fine. Maybe it's inclusion exclusion sort of thing on the edges. I think that would be, what, 2 to the number of edges, right? So initially, we want, you can do like n choose k. So if you have like n people, and then you need to pick k of them. How many ways are there to do it? Well, there's n choose k, but we've overcounted quite a bit. In fact, we've overcounted all of the ways in which you take at least one edge. So what is that? Well, minus for each edge. Pick both. Then plus for each pair of 2 edges. We've double undercounted them, right? So we initially didn't count them, then we added n choose k, which overcounted them. Now we're subtracting out each of them, but we subtracted out the same pair twice. Yeah, pick 2 edges. I think this makes sense, yeah. So this n choose k part is going to be a little bit tricky. Quite a few times it's going to be 0. But I think that's a non-issue. Alright, so it's Codeforces style, so I don't think we really have a choice. So we kind of like have to just code this. So we'll do that. Problem G. When I say we don't have a choice, I mean I have to do this rather than thinking about F for the moment, because I'm losing points on this. Actually, I'm not. It's educational style. But scoreboard suggests this is still a smart thing to do. No, it doesn't. Scoreboard just says this is a lot of code and people are too lazy / too slow to do it right now. But I think we're right here. What kind of people are getting it even? Ooh, that's kind of scary. Yeah, man. All right. Well, I think we'll just go for this one then. So, what do we need to do? We should read in the number of nodes and also the number of edges. Okay, so now we'll probably make an edge class. Okay, so now we want a bunch of nodes. Am I reading this input format right? This is the left and right endpoint. Okay, now we read all of the edges. Okay, so now nodes at A, or we just need to add a new edge. Edges at I equals new edge from nodes at A, nodes at B. New edge array, M is the number of edges. Yeah, okay. Nodes probably also want an index. So we have all of our nodes and all of our edges. Yeah, it's well, I guess let's just do this. So Boolean valid int. We can just do this int L R for an edge. L equals math.max from .L to 2.L. R equals math.min from .R to 2.R. Okay. So we have an issue with this strategy. Yeah, the fundamental issue is that the number of ways to like pick one edge that's illegal depends on the number of people there are, which can change quite a bit. Like we can't do this inclusion exclusion thing at every number of people we have left, because that would be too slow. So we need to do the inclusion exclusion in such a way that it is not specific to how many people there are. What would we want to count even then? If we have like which edges are alive. So what I was thinking of like doing is like some DP for like which edges. I suppose this isn't 2 to the n, it's only order number of edges, so this is only order like n edges. Might make it a bit easier. Yeah, I don't really see how to do it. It's only order number of edges because the edges are defined by the range for this node and whatever the range for this one is. Like the intersection of those two ranges is when this edge is relevant. In all other cases, it won't be relevant. And then the set of which edges are relevant as you increase the number of people that you pick will change order n times, because each edge it'll become relevant and then stop becoming relevant. It isn't obvious to me though how to count this in a way that is like not dependent on n. Oh, I suppose, what would it be dependent on then? It'd be dependent on n choose k or n choose... Well, it'd be dependent on n choose k, on n choose k minus 1, yeah, okay, n choose k minus 40. It's dependent on these 40 things. So if we know which edges are relevant, how many times do we know which edges are relevant? That would be, it's not really that important really, because it's only like, when the number of edges is less than like 18, then it gets very small very quickly. So it's pretty much only like 3 times, maybe 4 times. So we'll add a factor of 4 for that. So we do this roughly 4 times when it's big. Then we find these 40 values in 2 to the 20 time. We find 40 values. And then to evaluate this, we do three times 10 to the 5th times 40. That's our runtime. Yeah, that's fine. The runtime's fine. We want to maybe consider just like figuring out problem G. If this were rated for me, I would definitely just solve G rather than working on F. Yeah, in terms of like actually just going for best performance, solving G before thinking about F is the way to go. Okay. Yeah, I guess we're kind of forced into it. Sure. So, all right, what's the game plan here? We look through all subsets of edges. I suppose we just consider all ends, then find which edges are relevant. If we haven't calculated it, then calculate it for this group of edges. When I say calculate it, I mean calculate these 40 values of how much do we depend on each of these numbers. We know how much we depend on each of them, then we can figure out how that changes when n changes. Yeah, okay. Cool. So what do we need to do that? Probably a big DP array. Okay, so what does this actually represent? So DP at mask sub from K equals the number of times that sub from K, or that, I guess this is just the multiple of n choose K minus sub from K with like with the given edge mask. Yeah. So how many times might we want to do that? Not too many. DP equals new int array, 2 to the number of things by 60, I guess. Oh man, that's kind of big. Yeah, that's a little big. Is that going to be an issue? No, should be fine. 6, yeah, we multiply this by times 4, 256 megabytes, yeah. Okay, that's fine. Yeah. Fill DP with infinity. And then for int n people equals 0 and people is less than or equal to n, people plus plus. Int edge mask equals 0, I equals 0, I is less than m, I plus plus. If edges at I dot what is wrong with this? I know autocomplete. I spelled edges wrong. If edges at I dot L is less than or equal to number of people, and edges at I dot R is greater than or equal to the number of people, then edge mask plus equals 2 to the I. All right. So now we have this edge mask. So if dp at edge mask 0 is not equal to infinity, then continue. Otherwise, we actually need to calculate it. Okay, so this doesn't happen very often. Oh, well, you can just do the submask. This is just like sum over submasks. Yeah. So for int submask equals edge mask, submask is less than, or is well, let's just say true. Submask minus equals, submask equals submask minus 1, ended with the edge mask. So now we care about how many edges are we including. Boolean to, or should subtract. That's equal to integer.bit count of the submask mod 2. If it's equal to, equal 1. If it's equal to 0, then that's the same as like nothing. So we should add it. If it's equal to some positive number, we should subtract it. Yeah, okay. Then what else matters? The number of nodes matters. So we should probably have like a node array for this, or a Boolean array. We should just have an array of special nodes, maybe. There aren't that many of them. Okay, so for int I in special nodes, we can just say, oops, hit at I equals false. So now int n hit equals 0 for int I equals 0, I is less than m, I plus plus. If I and one left shift, or this is submask, and one left shift I, this is not equal to 0, then this matters. Yeah, so now we need to include this edge, then include this edge. So int person1 will be edges at I dot from dot index if not hit at person1, hit at person1 equals true, and hit plus plus. And same thing, but with the other edge. Okay, so now we have hit a bunch of people. So now we need to say dp, or I guess this is important. So yeah, so int array multipliers, new int array 60. So now dp at multipliers, or okay, no, so this is multipliers at n8 plus equals, depends on some stuff, so should subtract. So if we should subtract, then we subtract one, otherwise we add one. Yeah, okay. Sounds fine. This is all submasks. We do some stuff. Now what? Text is too big for me. I'm sorry, YouTube, but I can't even read this entire for loop. So now, once we've adjusted the multipliers, now you have to update the dp. For I equals 0, I is less than dp at edge mask length, I plus plus, dp at I edge mask I equals multipliers edge mask. There's multipliers at I. Yeah, okay, so now if the submask is equal to 0, then break. Alright, so that looks good. Yeah, so we do a bunch of stuff. Very good. And now we're done with this pre-comp. So now we need our nChoose K. Mod static long add long a long mod. It's Andrew He's birthday today. Happy birthday, man. Okay. Multiply, add, subtract. I think that's all we need. So now we need our factorials. Static long array facts, and then inverse facts. Facts equals new long array 10 to the 6. Inverse facts, new long array 10 to the 6. We also need fast expo. If the exponent is equal to 0, return 1. Long half equals tau base to the exponent over 2. If exponent mod 2 is 0, multiply the half by the half. Otherwise, return the half times the half times the base. Okay. Facts at 0 equals 1. So, well, I guess we can just, these probably don't need to be that big, right? It can just be this big, and then we're fine, and then we can just be naive. So we have the, this is the mod minus 2 rather. The factorials of everything and the inverse factorials of everything. Good. So now we just need n choose k. Static long n choose k. Here's where we have to be careful. Or int n is k. So if k is less than 0, then return 0. There's 0 ways to pick a negative number of things. If k is equal to 0, return 1. If k is greater than n, return 0. You can't pick more than 3 things if you only have 3. Otherwise, this should be handled actually. So otherwise, we can just return multiply factorial of n by multiply the factorial inverse of n minus k by the factorial inverse of k. Okay, I think that's fine. Now we actually need our answer here. So we would need a delta of the number of people. This will be n plus 1. These are all in a reasonable range, right? Yep, okay. For node n in nodes, n people delta at nn dot l is n plus 2 actually. Number of people is always at least 1, right? non-empty subsets, yeah. So now n people alive plus equals n people delta at n people. Okay, so now we have some stuff. So now, yeah. If it's equal to infinity, then we want to do this massive bunch of logic that calculates it. Otherwise, we just want to print the answer. Wait, that's, hold on a minute. Do that here, yeah. Okay, so how do we calculate the answer? Well, we use the factorials. We pre-comp in the beginning, right? Yeah, okay. So now, we just need the total. 4 into sub is equal to 0. 2 sub is less than... Wait, I'm saying n choose k. N will be the number of people alive. Oh, we have like some answer. We need some like total answer. So long answer equals 0. And then sys out the answer. Yeah, okay. So if n people alive is less than the number of people, then we can't actually have that many people, so just continue. Otherwise, we need to pick n people from n people alive. Okay. So the number to subtract is less than 60. dp at edge mask length 2 sub plus plus. So now total equals add. This has to be, we have to be more careful with this. Add the total to multiply something. What is this? This will be dp at edge mask to sub by n choose k. The n is constant. The n is just, no, it's not constant. The n is n people alive minus 2 sub. And then the k is n people minus 2 sub. Yeah, okay, so, but we have to do some more stuff here. So now, if n is less than 0, return 0. I think that's it. What are the chances this works, right? That's the golden question of the day. Maybe let's start with a simpler example. What is this number here even? The number of edges? Oh, yeah. No edges, huh? Well, that's pretty simple. So you can take this person, or you can take these two people, or you can take just this person, I guess. Yeah, okay. So, whoa, there are two people alive here. When n equals 2, there are two people alive. When n equals 3, there are also two people alive. Okay, that's fine, actually, yeah. Yeah, okay. So, long n choose k equals this thing here. So now considering 2 sub would be 2 sub, n choose k will be n choose k, and then dp value will be dp at edge mask by 2 sub. Two times 1, huh? That should be 2. There are 2 ways to have one person alive. Oh, duh. Ants plus equals total. Three, it's a bit surprising. 2, it's even more surprising, but I am gullible enough to submit. Is this a bad idea? Yeah, it's a bad idea. It's very openly just not the best idea. Because there's just so much code here and so little of it's being tested. But, you know, there's always the chance. It would make my day if this were right. If it's not right, it's not the end of the world. Test 12? Oh my goodness. Test 12 is so late. Man, test 12, really? Test 12 is so big. Makes me feel like it's a mod issue even, not a... Ah. I think I literally just did the same thing last contest. I think I just... Man. I swear I did the same thing. If it wasn't last contest, it was like 2 contests ago. Super recently. It's just I'm adding to some total and I don't do it under mod. The 7-second time limit is very nice of them. I'm a fan. $34, looking good. Looking good. Or the standings. We're gonna be not terrible if we get this right. To be honest. 64th place, 72nd test. It's right. Come on, it's definitely, you know it's right. It's so right. How are my friends doing? We got it. 17th place, not bad, not bad. Yeah, alright. Seems pretty average, I guess. Yeah. Alright. So then, this is what's left, but I do have some stuff I have to do unrelated to Codeforces. So let's read it, think about it for a bit maybe, and then we'll do solutions. How about that? So we have an integer value x and a string of a bunch of digits. Yeah, this is, so we've got the sum of digits of some substring. Okay, yeah, so what's the problem again? If no substring is divisible by x. Well, x is fixed even, right? So we know what these substring sums are. Yeah, I feel like it's a DP. I feel like the idea is do a DP and then do like just space saving, because most of the states are like, you can do a DP where your state is the mask of like which of these things matter and then what your position is. But like the observation is like most of the masks just either aren't gonna show up or aren't relevant. Like, there are just so many things that can't happen. Most of the time, if there's a 1, you have to delete the 1. Oh, wait, yeah, if we get rid of 1s, then we only care about the previous 10 things, even. So yeah, it's n times 2 to the 10. We just care which of the previous 10 things did we delete. Yeah. Alright, so I don't actually have time to code this, but I'll go over it in the solution video. So let's just, I guess, make sure we have the details. So you need to know what position you're at and which things you deleted. Then your transition is either you can delete this thing or not. The sum you can pre-comp if you need to. I guess you can just do probably order 20. Should be fine. So you're at, that's 2 times 10 to the 7. That should be fine for your generous 2-second time limit. You're within 10 times the time limit, so you're fine. So you just see for each mask, each things you previously deleted, what your sum is. If your sum is X, then you say, okay, this is impossible. What's the restraint? You also need to see what all of the previous substrings are ending at yourself. So that's a bit tricky, I guess. Yeah. How do you do that part? So there might be this thing might sum to K. So you need to make this like either not sum to K. How much harder is this problem than the other one? It's actually even harder. Odd. Yeah, so you need to make it so that there aren't any subs, like any substrings that exist don't sum to the right value. Or none of the substrings within it end up working. This sums to a factor of K. Well, this whole thing sums to X. So when we're here, we see like, okay, this can't end up working. We have an issue with these ones. If we have these 3 that are still alive, that means the soonest we can actually start is here. Oh, can we do, since they're all small, we can probably do some shenanigans with like figuring out if it's legal. So we are just checking the previous 10 things, right? Oh, it's not just a matter of the previous 10. It's more difficult than that. It's like what the previous 10 are. Yeah, it's like the previous values that sum to the correct value. It's not just the previous 10 positions. Because the previous 10 positions, if you didn't pick any of them, that doesn't tell you anything about your sum. So that's hard to bound, I guess. But it's probably not that big. Like you care about the previous included values, what they were. There aren't that many if you handle the 1 case separately. There aren't that many of them, I'd imagine. Yeah, okay. So, well, what about that? Maybe, so there aren't that many. So now we have like some small array that's of length at most 10. We would like to preferably very, very quickly See, is this illegal? Well, we can even pre-compute that. If we have this array, we can pre-compute that, yeah. Whether it's illegal, maybe using like some hash. So this shouldn't be that hard. I guess this whole thing comes down to the analysis of there aren't that many arrays that look like this. There aren't that many arrays whose sum is 20 or less that also have no ones in them and only have digits 0 through 9 or 1 through 9. Yeah, so digits, how many arrays are there? Digits 2 through 9 that sum to at most 20? Probably not many. So then what's your DP state? I mean, probably about 1,000, right? That's what the goal is. Like, surely it's fewer than 2 to the 20, but it's not really that much. It's a lot less, actually. Probably. Yeah, I'd say it's like 3 to the 10. Worst case, how big is 3 to the 10? A little bigger than I'd like. I don't know. Maybe the runtime's tight. It's hard to tell without actually like writing a program to just calculate that number. Well, anyway, so you've got that. So your DP state is like what the previous things look like. So the relevant array. And then what else matters? Your position matters. So what can you do? You can either skip this, or this might be required, in which case you might be able to take it if that leads to a legal array. Both of these you can do in order 1. Okay, good. So yeah, let's go over solutions. I would love to be able to solve this. 20 minutes might be tight. I don't know if I can do it in 20 minutes. Seems like quite a bit of code. But yeah, I would love to be able to actually at least try, because lots of other people are getting it. So yeah, it's a doable problem for sure. It's not too bad. Let's go over solutions though, because I got other stuff I have to do, unfortunately. Yeah, okay, so problem A. So you have a binary string, and you're gonna make another binary string for each character in this binary string. If you can go k steps left, then that binary string that was k steps left should now be a 1. If you can go k steps right, it should be a 1 as well. So the question is, can you undo this operation, please, given k and the resulting binary string? So this isn't actually anything, but if we look at one of these examples, if you take, wait, no, this is problem C. Problem A is you're given some set or some binary string that's an odd length, and you have to find some other binary string that's similar to all substrings of length n. But one fact that's interesting is that this middle character right here is included in all of the substrings that you have to be similar to. So as long as all of your characters match this middle character, you'll always be similar to the other one in at least one position. That is, at least one position will match. So we just find whatever this middle character is, and we just print that n times. And that's the solution. Okay, so that's problem A. Let's move on to problem B, RPG protagonist. I don't remember this problem at all. Yeah, this one, okay. So the idea behind this problem is you want to steal as many things as possible. Oops, it's like kind of a knapsack DP sort of thing. Except this is a simplified knapsack because you only have 2 types of things you can steal. So you can either steal swords or war axes. There are a fixed number of swords, fixed number of war axes. Each sword has a certain weight, each axe also has a certain weight. But to make things more complicated, I guess, instead of just one person stealing it, you have 2 people who are both trying to steal it. So since you don't value any thing about the sword or the axe other than like the number of them that you take. Whatever one is lighter is the one you're going to want to take more of. So if a sword is like the one you should prefer, right? So if a sword is lighter than an axe, in all other ways it's similar, and you want to take as many things as you can that sum to a certain weight or less, then you might as well take a sword instead of an axe, because if you were taking an axe instead, you could just replace that axe with a sword. So the only reason to ever take an axe is if you run out of swords, assuming swords are lighter. If they're not, we'll just swap swords and axes, swap the definitions. So now we're taking whichever one is lighter. We want to take as many of those as possible, and then after we run out, we want to take as many as possible of the other one. If it were just one person, that would be easy. But since we've got two people, we've got like a follower that's also going to help us rob this blacksmith. We don't necessarily know how we want to divide up the light weapon between the two of us. We might, if we're going to have to take some heavy weapons, we might want to like level these out in such a way that we can get some extra weapons and the rounding works out in a convenient way. And that's hard to predict ahead of time. So what we can do is just, since there aren't that many swords in total, we can just brute force how many swords we take. Then we'll give the rest of the swords that we can still have to our Padawan, and then we'll distribute the axes with the space we have left. We'll just greedily take as many axes as possible. So I forgot to show code for A. Code for A just looks like this. So you just print the same thing n times. Code for this problem, this part just swaps the swords and the axes if swords are lighter than axes. That's just what this is doing. C++, this is like 3 lines. And now what this does is it just says, this part means if we can't actually keep the number of swords that we're brute forcing, then ignore it. Otherwise, this is how many swords we keep, the minimum of the number of swords this is how many swords the Padawan keeps. So it's the minimum of the number of swords that are left after we take our share, and the number of swords the Padawan can carry. Then this is how much weight I have left and how much weight he has left. Then we just calculate how many axes can each of us keep. For me, it's just the amount of weight I have left divided by the number of axes. Divide by the weight of an axe, mind with the number of axes. For him, it's the same thing, except we have to say we can't like both take the same axe. So we have to subtract out the number of axes we took from the number of axes that are left. And then we just find the maximum over all possible ways of stealing some number of swords. All right, cool. That's problem B. On to problem C. This is the problem that I initially thought problem A was, which is you have some string, and you're going to modify that string by, you don't modify it, you create a new string, which is if you can go X steps right or X steps left and land on a 1, then this character is a 1. If both of those will land you either out of bounds of the string or on a 0, then this character in your string will be a 0. Let's look at this input, because I think this is a good example. So if we look at this middle, or this, I guess this 4th character here, that corresponds to this character here. In this example, X is equal to 2. If you go 2 spaces left or 2 spaces right, you end on a 0. But if we look at this last character here, you can go 2 spaces left and you end on a 1. So that's kind of how this example works. The way you can code this, like actually implement this, well, sorry, first of all, what's the goal of the problem? The problem asks you if you're given this string here. Yeah. You're given, this is the original string that you have to print, and this is the string you started with. So with the string you have to print, if you start on a 0, then if you go 2 spaces left, you end on a 0. You go 2 spaces right, you also end on a 0. So the question is, if you, or what string do you have to start with so that you end with this string here? So there are a couple observations. The first one is, if you're ending with this string and this position's a 0, that forces some other positions to also be a 0. If you take 2 steps left from this, you have to be on a space that's a 0. If you're on a space that's a 1, that means this would be a 1. Right? Let's draw this on the whiteboard. It might be a bit easier to see. So if you've got like some positions like this, then let's say x equals 2 again, right? If you're at this position here, the final value of this position would be a 1 if either this or this were a 1. But if the final value here is a 0, that means both of these needed to be a 0. So these are both forced to be a 0. That's the only time anything's forced. If this was a 1, you know, one of them might be a 1. In fact, one of them has to be a 1. They can't both be 1s, but you don't really know which one's the 1 or whatever. But if you ever have a 0, it forces other things to be 0. So what you can do is you can initially fill everything with 1s. You can say everything's 1 and everything is a 1 initially. Then after that, you walk through the array. Every time you see a 0, the things that it would force to be a 1, or the things that would force to be a 0 as well in the original array, you make those zeros. So if this were a 0 here, then you would walk 2 backwards. You'd say, okay, that's out of the array, so I don't care. But if you walk 2 forwards, you'd see, okay, this one is in the array, which means this is forced to be a 0. It's either a 0 or this is impossible. So we make it a 0, and that's fine. And we keep doing that for every position in the array. Then at the end, all we have to do is just go back and see, does this match up to the array we're supposed to generate? So you can just try generating it from this array. If you wind up with the correct thing, then you're set. Otherwise, it's impossible. Because all the decisions we made were entirely forced. We didn't have any say in the matter. We weren't being smart or something. Like, if it were a 0, that means the other two positions needed to be a 0. So yeah, that's the problem. The code, what does that look like? Initially, I have an answer that starts as all 1s. And then if going back some number of positions, or if I'm a 0, and going back some number of positions is still in bounds, that means that position has to be a 0, because otherwise I wouldn't have been a 0, I would have been a 1. Same thing with going forward that number of positions. That would make it, that would make me a 1 as well, so it has to be a 0. Then this part just generates the array like we're told to in the problem, runs in linear time. And then finally, if it works, I print -1, or if it doesn't work, I print -1, but if it does work, I just print whatever answer I generated. Okay, cool. So yeah, that's problem C. Let's move on to problem D, zigzags. I thought this problem was pretty easy, but I don't know. Like, I got it in 3 minutes, so I thought it was pretty easy. Definitely easier than B, in my opinion, but that's fine. So how does it work? So the problem says, it's called zigzags because they make a zigzaggy pattern. You want to see how many like sets of x, y are there in the array? In some array of n numbers, where n is like 3 times 10 to the 5th. So you want to count the number of these things. Let's say we know where this position is and where this is. So if we know this y here corresponds to this position in the array, this x here corresponds to this position in the array, we'll brute force these. So our runtime is going to be order n squared. If we know these two positions, we know this is going to be a y and this is an x. We want to say how many x's are there in this prefix of the array that come before this. Similarly, how many y's are in this suffix of the array that come after this x. So what we can do is when we brute force this, instead of like going like usually you do like for I equals 0 all the way up to n, and then for j equals 0 all the way up to n, or j equals I guess, I plus 1 all the way up to n. Instead of doing it like this, that would have like the I go like this and then the j go forward like from that. You can have the I come forward from the left and the j come forward from the right. Then when you do this, you can just keep track of how many of each number have you seen behind you. So that's the idea. So just to walk through an example quickly, you would have this j, oops. So we do like 2 nested for loops, but this first pointer will walk this way from the beginning, and the second pointer will walk left from the end. When we do that, we can keep track of how many of each number have we seen, and when we're here, we just want to say how many of those are x's. So we just look at how many things have we seen, and for like we have an array of how many of each value have we seen, we just say how many x's have we seen, and the things that come before y. And then we do the same thing for the other side. Code-wise, it is very simple. We just keep track of how many things have we seen to the left of our left pointer and also to the right of our right pointer. And yeah, we just multiply them together. So we get to pick any of the x's in this side. We can pick any of those to match with this x. We can pick any of these to match with the y. We increment our answer by that, and then we increment when we move the pointers, we add this thing as something that's to the one side or the other of our pointer. All right, cool. That is problem D. Let's move on to problem E. We have a multi-set of several integers. What's the problem again? Oh, yeah. We have to delete all elements from the multi-set. Yeah, okay, so here's the problem. So we have, basically we've got like some array. And here is how it works. So we've got like, maybe the array is 1, 3, 100, 3, 2 or something. 3, 2, 3 maybe. So we can do two different types of things. The first thing is we can pick some continuous range of the array and subtract 1 from every element in that range. Maybe we pick this range here, the entire array. After we subtract 1, we have something that looks like 0 to 99, 2, 1, 2. Now we can do this again if we want. Then we subtract from that array. Now we have 0, 1, 98, 1, 0, 1. We can do it again. We can do this part here. But we can also do this other operation, which is we can pick one element and we can subtract as many things as we want from that particular element. So we could take this 98 and we could turn it down into a 1. Then we would have 0, 1, 1, 1, 0, 1. The question is, what's the fewest number of operations in order to make this array all zeros? So I've kind of reworded the problem a little bit. I think this is an easier version to understand, but maybe it's one step closer to the solution, which is why they chose to go with their more, or like less intuitive, but more hidden version of the problem, because it doesn't spoil the solution quite as much, maybe. Yeah. So how do you actually go about doing this? Well, you can like make the following observation. Let's imagine we look at the array from the beginning to the end. So I'll draw them as if it's kind of like a histogram sort of shape, because I think that makes it easier to think about. Maybe it's something like this, or maybe... So really what we're doing is, as we go left to right, as we go left to right, we will like pick this and we'll start deleting things like this at this height. We have two choices when we're at a particular position. The first choice is what we'll do initially, which is we can like increment the part that we're deleting to this height. And now we can get these for free for as long as we want, until the height of the bar that we're at is too low, in which case we have to stop incrementing this, or stop like getting these things for free. Incrementing it costs 1, because that corresponds to starting a range of things that we delete at this position. So we can like start deleting a range of things. That's one operation we can do. The other one is we can just delete everything here. That also costs 1. Now, we wouldn't actually increment, like when we do that first operation, I said we can start one range, but really it's pretty clear how many ranges we can start. We can either start enough ranges to delete this entire column, or if we don't do that, then we can just delete the entire column. There's no reason to do anything else. So there are only like two possible transitions, I guess. I guess I'm spoiling the answer. It's a DP, if you didn't see that one coming. So it's a DP. But the first thing we're gonna do is like, we're going to conceptually delete this entire range, we're going to delete this entire range, then we're going to delete this part here. Those are the optimal transitions in this case. How do we do this? So we start initially deleting nothing, and now we increase the part that we're deleting to this here. Now we're here and we're deleting this part. We want to increase it to this position here. We keep going, we delete this up to here. Now the height of our, like the height of the array will decrease. So we have to lower it down to here, which is free, but it makes future decisions more expensive maybe. Now for this position, we could consider increasing it all the way up to here. That's one possibility, but it turns out that's more expensive. And in this particular case, we would just delete this here. We would try both of them. That's part of how DPs work. You try like all of the possible choices that you would make, or that you would want to make. In this case, we try both of them, but one of them winds out being suboptimal. And then we continue going like this, and we get these for free as well. So yeah, that's kind of how the DP works. More formally, it looks like this. We have a DP at what the current height is, the like height of the things that you're deleting. The height for free, I guess, we'll call it that. And also which position you're at. Now, you might initially think this isn't going to work because the bounds here are, this is up to 10 to the 9th, this is only up to n, or this is up to n. So your total runtime is going to be too big. But it turns out the only heights that you actually care about are heights that are also positions in the array. So you have two options. The first is you can coordinate compress. The second is, instead of storing what height this actually is, we can just store what index is it that corresponds to this height. So yeah, that's the idea. You store this, instead of being 10 to the 9, this is really just order n. And you just store what index in the array are you the same height of. To handle the 0 case, you might also be height 0, for example, in the beginning of the array. In that case, what you can do is you can just add a 0 to the beginning or end of your array. I added it to the end, and then you just pass in that index for the height for free that you start at. What does that actually look like? Well, this is problem E. Yeah, you just do this. I make my array 1 bigger here, and I return 0 if I'm at the end of the array. Initially, I start at the height of 0, which is at the end of the array. So this is, I pass in the index. This is which index I'm at. This is the index of my height. So the array at this index will correspond to what my height actually is. To actually do the DP, there are two cases. Either this next thing is above my height. If it's above my height, what I'm forced to do is either buy some more, like start creating horizontal lines in order to like catch up to my height, because I have to make this 0. The other option is I can just delete this whole chunk. So this is deleting the whole chunk. It just costs 1 move, but your depth doesn't change. The other option is you can pay for the difference, but then you have this height for the future. So maybe it's helpful. You can't really tell without looking ahead which one of these is better. If you go down, then you have to just decrease your current height, or you decrease your height to whatever your current height is. That's free, but that's the only choice that you have that's actually meaningful. All right, yeah, that is problem E. So 2 more problems real quick. Let's do problem F, x prime substrings. So I didn't actually solve it, but I can give you a general idea of the approach I would take, and maybe that'll be helpful. So what the problem is you have an array of characters, and are samples good? I didn't even read them that much. Yeah, I don't know, maybe. You've got some array of characters, and it's just like a bunch of characters. These aren't zeros, they're just circles. All of the characters are 1 through 9, which makes it easier. And what you can do is delete some number of characters, but you want to delete as few as possible, so that any range that sums to k, like if the sum of the digits sums to k, then there's no substring within that sums to a factor of k. So you want this to never happen. Yeah. So I'm not sure what the exact solution is to this, but one thing that you could try is if you have any ones in the array, then wait, why is this 13? Why does this 13 work? Why is this legal? 13 and 1. Why does 1 not break it? Oh, because 13 doesn't sum to 13, it sums to 4. Yeah, that's why. So, sure, if you have any 1s in the array, then, like, you can't ever have any substrings that sum to your target. So that's, like, one thing you can handle. If you handle that, then you've gotten rid of all of the 1s. So now, if you have an array with no 1s, I won't go into too many details of that. Basically, you just like store, yeah, you can do like, maybe it's a bit more tricky. I don't know. I don't know if like full details on this problem. But the idea is like, or the idea that I'm thinking about at least, is if you can somehow handle getting rid of all of the 1s, then you're left with some array that either has no substrings that sum to some value, or you're left with some array that has no 1s in it. If it has no 1s, you can do a DP where you store what are like the previous values that sum to something less than 20. And then also what index are you at. So the size of this is just the number of arrays with digits 1 through 9 in them that sum to some number that's less than 20. I don't think there are that many of those. I think that number is pretty small. And then this has a transition of 2. So there are two options. Either you can take this next thing, or you can skip the next thing. And this like costs 1. The second transition costs 1. You can also pre-comp whether or not it's legal to take the next thing, because you have this state fixed here, and then there are only 9 different things you could take next. So in however big this array is times 9, then you could handle that pretty quickly. I guess the part that you have left is what's the minimum number of things you have to delete, so there are no subarrays that sum to some given number. And that's, I guess I haven't worked out the details there. Okay, last thing, which is problem G, which was quite a good problem. I really enjoyed it. And here's what the statement was. So yeah, so you have a bunch of like, you're gonna create an army, and you've got a bunch of like people, some of whom dislike each other. So you might have like these people right here dislike each other. You have a bunch of other people who are maybe these dislike each other, and maybe the rest of the people are just fine with everyone. The total number of edges you have in this graph, where an edge is 2 people who dislike each other. The total number of edges is at most 20. Since it's small, we should be looking at like how can we abuse that, because it's very small. So we can maybe do something like exponential with it. So the number of edges is very small, but in addition to that, we know the number of people can be big, but there aren't that many people who have an edge connected to them. Since there are only 20 edges, that means at most 40 people have a degree that isn't 0. So we can look at that. But also, okay, I didn't finish explaining the problem, which is each person has some continuous range of the number of people who they would be happy working with. So this person might be fine going on a mission if the mission has between 3 and 7 people. This person might be happy going on the mission if it has between 1 and 4 people, and everyone has their own range. Now, the idea behind the solution is all of these constraints for different people get kind of hard to handle. So instead, what we'll do is just, let's say we'll brute force the number of people that are going on the mission. Then we can ignore all of these constraints, and we have like kind of a simpler version of the problem, which is if we know how many people we're actually going to choose, we've brute forced that value. We now know which people are candidates to actually go on the mission and which people aren't. So let's say, for instance, this person right here does not want to go on the mission, and maybe this person doesn't either, and this person doesn't either. The rest of the people are happy going if we pick 3 people. So we're going to do this a bunch of times. This number of people that we're going to pick, we brute force. From that, we have some set of all of the people that we're okay taking. Now, this set will change quite a bit. We can't iterate through all of the people every step, because that'll be n squared. So what we can just do is keep track of when someone becomes legal and becomes illegal. We can also do the same thing for each edge. So an edge is only legal if both of the people in it are okay. If the edge isn't legal, then then we just ignore it. So now the question is, like, for this subproblem, how do we count how many groups are there that contain 3 people, where we don't ever pick 2 things that have an edge between them? Initially, we can count it using inclusion-exclusion. So in total, we have 7 people. So we have 7 choose 3. Like n choose k, 7 choose 3. There are that many ways, but we've overcounted some. In fact, the number of things we've overcounted is, well, if we pick this edge here, then we aren't allowed to pick this, right? So we need to subtract out picking these 2. The number of ways of doing this is, well, we have to pick both of these, then we can pick, we have like a free choice for who our third person is in this group. So this is minus, we have 5 people left, so 7 minus 2, choose 3 minus 2. So that's one thing that's illegal. Any other single edge would also be illegal. So we can do the same thing for any other edge. We do this like a bunch of times. So this thing happens like several times. And what we're going to do is like brute force every edge. But if we do that, then we've like kind of over double counted. So we said it's illegal to pick this edge and also any other person. Maybe it's legal to pick this edge and this person. In other words, it's illegal to pick these 3 people. But we also said it's illegal to pick these 3 people when we picked this edge with any other person, including this edge with this person here. So we've now said it's illegal to pick these 3 people in 2 ways, which means we've subtracted out the same thing that we double counted 2 times. So now for every group of 2 edges, we have to add that back in. And then we'll just have added back in too many times every group of 3 edges, so we have to subtract out every group of 3 edges, then add back in every group of 4 edges, subtract in every group of 5 edges, etc. So just flip-flops. But yeah, so the runtime here is going to be 2 to the number of edges in order to check this once. Now, we're going to do this every time the set of legal edges changes. The total, like the set of legal edges will change 40 times. But our total runtime isn't actually this bad, because this is assuming that m is equal to 20. It's only equal to 20 in like one of those steps. It's only equal to 20 if we add 20 times and then remove 20 times. So it's not actually this bad. It's actually like better than this by some amount that's kind of hard to quantify, for me at least, for my small brain. But if you're a math genius, then maybe that's intuitively like 2 to the 21 or something. I don't know. So every time the edge set changes, we'll recalculate all of these values. Now, it gets a bit more tricky because we can calculate all of these values. So it's like plus 7 minus something minus 3, choose 3 minus 3, and then we have some other chooses in this series as well. These are also multiplied by some constant. So it gets a bit more complicated as well, because the 7 might decrease or increase by 1. Also, the 3 will increase by 1 every time as well. So this is assuming we're choosing 3 people to go on the mission. We might also choose 4 people to go on the mission. Well, if we do that, all of these numbers will change. Which means if we don't do something smart, we're going to have to do another 2 to the number of edges, which will be way too slow. So to handle that, what we can notice is if the edges themselves don't change, if the set of edges that are legal doesn't change, the multipliers on all of these chooses don't change either. The multipliers are what's really hard to calculate. The actual choose values we can calculate in order 1. So it's this multiplier thing that we want to avoid calculating as much as possible. And the multipliers only change 40 times in total. So what we can do is just not worry about the multipliers most of the time. Only worry about them when an edge gets added or removed, when an edge gets made legal or illegal by us changing the number of people we're bringing on the mission. And then we can recalculate, since this series is only like 40 long, we can just walk through each 40 of them for every possible number of people. So this is what the code looks like for that. Well, it's a bit complicated, I guess. Yeah, it's kind of hard to explain. But this array is the array of people that we have chosen by at least one edge, so the people that are adjacent to at least one of the edges we've picked. And I just, the special nodes are just nodes with a non-zero degree. So any node that is connected to an edge, I just add to this array. It might be in it multiple times. Then I keep track of how many people would be willing to go on this mission if there are this many people going on the mission. So if we have a mission of 3 people, how many people would be willing to be one of those 3? Then I brute force this n people is the number of people going on the mission, and n people alive is how many people would be willing to go on a mission, assuming n people went on the mission. So every time this hits someone's minimum number of people they'd be willing to work with, then I add to the number of people alive, and then it'll subtract from it when it hits the maximum number of people alive as well. Now I get a mask of which edges are legal, and if I've seen this edge mask before, then I just ignore it. I don't do this whole 2 to the number of edges thing. Which means I'll only do this actual 2 to the number of edges loop a total of like 40 times, but most times it'll be fast. It's only like 2 to the 20 like once or twice or something. Then at the end, once I have calculated all of my multipliers, I've stored them in this DP table, then I just add this to my total and then print the answer. So now this interesting part is, how do we calculate the multipliers? Well, we look through all submasks of this edge. This is the inclusion-exclusion part, it's 2 to the n. And if you're not familiar with inclusion-exclusion, I'm not going to teach like the whole thing here, so you should probably like look that up separately. It's a good thing to know. It's used for this problem, and there are probably like really good Wikipedia articles on it anyway. So yeah, go for that if you're trying to solve the problem. But you do inclusion-exclusion on it, and we're doing all of these submasks. You add if the parity is even, subtract if the parity is odd. And then I count how many people are hit by at least one edge that's in this set that I'm considering. Each person that's hit is forced to be picked if I'm going to pick this edge set. So for each of those people, like, I have to subtract 1 for each of them from the n choose k. In my picture here, I had like 7 minus 2 and 3 minus 2. This 2 is because there are 2 people that are adjacent to some edge. So this is what this index here is. This number hit is how many people I hit. So that's why the number of people hit is important. And yeah. Yeah, that's the idea. At the end, I reset the people which were hit for the next time, but I do it faster than linear time, just in order 40. Yeah, that's the idea. So I either add or subtract 1 to that multiplier from this mask. And then I print the answer. All right, so that was educational round 94. I enjoyed it. Let's see, how did I do? '26th place. Not bad. Not bad. Yeah, could have been worse. Could have been worse. Nice job, geothermal solving set. Well done. It's interesting. I should upsolve F sometime when I have time. I'm having a very busy week at the moment, but we'll figure it out. Monogon wasn't quite able to get this. Time limit exceeded test case 90. That is unfortunate. Uh-oh. Yeah, I wonder if it's an actual issue or like just like a stupid thing. Mine ran with plenty of time if I remember it correctly. Well, I wouldn't call that plenty of time. It's over half the time limit. So I don't know. Anyway, I thought the problems were good. I enjoyed it. I thought it was a good contest. Maybe B was harder than C. So maybe B and C should have been swapped. So yeah, I guess this was a harder B than it should have been. But it was reasonable, I think. Not the end of the world in my opinion. Still a good set. I hope you enjoyed it as well. And I hope you enjoyed the problem solutions. Hopefully they were helpful. And if it was rated for you, I hope your rating went up. Hope you had a positive delta. So yeah, that's all from me. Thank you for watching and have a great day. Goodbye.